So welcome back to our second lesson on electrostatics or static electricity. So what we're going to start off with is a quick do now to give you an idea of how you're grasping the concepts. Okay, so a plane has just landed and parked at an airport. So what I want you to do is to pause the video and work through the questions, and we'll come back in a few minutes to see where you're at. Okay, so welcome back. So this plane's just landed. So your job was to explain why the plane may have become charged electrically, and then there's a consideration about this refueling of the plane, what's the main safety precaution associated with it, and explain what may happen if the safety precaution is not taken. So a possible reason why the plane may have become electrically charged is it may have been struck by lightning. Now, lightning essentially is electricity, so it's all negative charge. So the plane overall, if it's been struck, will have an overall negative charge. The amount of negative charges will be larger than the number of positive charges in the plane, or on the plane surface at least. So this plane needs to be refueled. So the main safety precaution is the fact that you've got this excess of negative charge. You've got your tanker full of highly flammable fuel, which is electrically neutral, okay? And what will happen? Well, it's quite possible this excess negative charge will jump in the form of a spark onto your tanker, spark with fuel, massive explosion. So the best precaution you could do is to earth, usually with a copper wire, your tanker, so the excess electrons or negative charge go through the copper wire down to the earth rather than causing a spark. Right, so today's lesson will essentially focus on something called the electrical field. An electrical field is a region where a stationary charge experiences a force. It starts to move because Newton's first law, force equals mass times acceleration. Newton's second law, force equals mass times acceleration. Okay, and so electrical charges create an electrical field in the space around them. Other charges in the field experience electrical forces. So therefore, depending on the direction of the field, the forces can either be attractive or repulsive. So now let's look at electric field lines in more detail, what they actually represent. So an electric field line is a line in an electric field so that the tangent to the line at any point gives the direction of the field at that point. Now, if you don't quite understand that sentence, we're going to go through it in a few moments to try and clarify it. The important thing to also note is that the intensity of the lines gives the strength of the magnetic field. So I'm going to also deal with that point very soon. So that first sentence saying that the tangent to the line at any point gives the direction of the field at any point. So here we have an electric field in red, okay, the electric field line. And the direction of the field is going to be the tangent to that line. So that's actually illustrated by that blue point there. Okay, that's a tangent to the electric field line, which actually gives the direction of the electric field at that particular point here. Okay. So the second point says that the intensity of the lines gives the strength of the field. Okay, I'm just going to illustrate that with two examples. So here we have a particular electric field going from left to right. Okay, so because they're close together, that gives an illustration that that particular electric field is strong. Whereas as if they were more separated apart, it illustrates that the electric field strength is actually weaker. Okay, so now moving to an illustration of a uniform electrical field. So say you have two plates. One is positive and one is negative. So a electrical charge of X will be moving in the direction of that field at point X, and it's uniform because the distance between the electrical field lines is the same. So a uniform electric field is produced by two metal plates, for example, in a battery, when they're connected, say, with a terminal where the positive charge is under the influence of force and moving towards the negative plate. And if we're to illustrate that actually visually, in that particular case, at point X, the direction of that point charge at X is illustrated by the red arrows in the diagram on the right. So now we're looking at the individual point charges. First, the electric field produced by a positive charge. The first thing you will notice is that the direction of the electric field is away from the positive charge. Conversely, for a negative point charge, the electric field is moving towards the negative charge. So in convention, in physics, electric fields always move from positive to negative. The other 2 points I wish to illustrate are that for both positive and negative charges, the strongest field is closest towards the charges because they are closer together, the electric field lines. And conversely, they are weakest the further away you get from the charge, as you can see from the electric field lines getting further apart as you move away from the charge. This makes sense when you think about it. If you have a positive charge moving towards a negative charge, you feel more attraction the closer you get to the negative charge because the electric field is growing stronger with decreasing distance. Okay, so finally let's look how the electrical fields interact in terms of 2 point charges. So you can see a positive and negative charge. You can see that the electrical field direction is going from positive to negative, and there's a strong force moving towards the negative point or negative charge, and that's why we have this force. This is why we experience this force between 2 point charges and the attraction. Whereas for 2 like charges, like positive or negative, you can see that the electrical fields actually cancel out, and there is actually a repulsion from these 2 like point charges. The other 2 examples are you've got a point charge and a negative plate, so or a negative point charge and a positive plate, and the electrical field created by the positive charge near a metal plate. You can see there is a clear attraction to that point charge to the negative plate, again in the direction from positive to negative. And finally, the classic example of the uniform electrical field between a positive and negative plate. So between 2 plates, it's a uniform field. The distance between the lines of strength are the same, whereas in the case of the point charges and the point charges with the plate, it's a non-uniform field. There are areas where the field strength is stronger and areas where the field strength is weaker. And that is enough for today. Tomorrow, or the next lesson, we'll move on to calculations involving field strength.